Question 8, 8.1 says we have to determine f prime of x from first principles if f of x is equal to 1 over x. Okay, so something you can actually do first before deriving it is you can use the actual rule of derivative to derive this function first, and just to make sure that you have the right answer, so that when you derive using first principles, when you get your answer, you can compare it to that. So we have f of x is equal to 1 over x. Okay, what we can do is prepare this to be derived. So f of x is equal to, the problem now is x is on the denominator. It shouldn't be on the denominator, it should be on the numerator so that you can properly derive it. So when you move it to the numerator, there's a consequence for this. It means that your exponent, which originally was 1, right, it's going to become negative. So it's now negative 1. And then now it's ready to be derived. So you can say f prime of x is equal to 1 times negative 1 is negative 1. And then x to the power of negative 1, subtract 1 from that. So you have x to the power of negative 2. Then if you put this in a way that its exponent is positive, this is just going to be negative 1. Since this is on the numerator and the exponent is negative, you bring it to the denominator, which makes the exponent positive. So we already know what the answer is now. And let's just go ahead and derive this using first principles, okay? From first principles to see whether we're actually going to get to that answer. So let's go ahead. When you are deriving from first principles, you're going to use this formula. So this is really the formula for the gradient of a function. We have f of x and we have f of x plus h. So we have to first find f of x plus h. So I'm going to go ahead and find that and say f of x plus h is equal to, meaning wherever I see x in my function of f of x, I'm just going to replace it with x plus h. So I have 1 over I see x. I'm just going to say plus h. Okay, so really just adding an h to the x. So now we know what that is, and we can go ahead and use our formula. So we're deriving, we're going to go ahead and say that this is equal to, and we're saying the limit as h approaches 0. You'll keep saying this until you get to the substitution. So this is f of x plus h. So we put 1 over x plus h. And then minus f of x, right, which is 1 over x that we have there. And all of this is being divided by h. Now, this looks quite complicated, and you don't have to write it like that. What you can do is the numerator, write that as one term, right? So I'm going to leave that as 1 over x plus h minus 1 over x. And then I'm dividing by h, so divided by h. Since these are fractions and this is not a fraction, we can make it a fraction by putting it over 1. Okay, so that's what we have. And then this is equal to, we're still going to have the limit as h approaches 0. And now we have to work on this fraction. So do you see that you're subtracting in a fraction? When adding or subtracting in fractions, you need to make sure that the denominators are the same. So how would we make the denominators the same? If you look at these fractions separately, the only way to make the denominators the same is to really multiply them by each other's denominator. So this one you'd multiply by x. And so what you do on the bottom, you must do on the top. This one, you would multiply by that x plus h. So times x plus h and times x plus h, right? But of course, as like that. So that's actually what's going on there, because you can't multiply this one by h. It's not going to work. If you multiply it by h, and I've seen students say multiply by h because they see a plus h here. The thing is that's going to become an xh. So that's not the same thing as x plus h. So that's what we do there. And so our common denominator is going to be, as you can see, since this is two terms being multiplied by one term, you have to write it as x times x plus h. That's your common denominator. And the numerator that we will have, let's just be very careful here. 1 times x is just x. That's fine. But please note that we have a minus here. So if we have a minus first, and then we have this, you see, it's the 1 times the x plus h. Since we are multiplying by something that has two terms, we still have, if you look at it as if the 1 is still there, it's really like 1 times x plus h. You see that now that negative is going to affect what you have in your brackets. Okay, so that's kind of what's going on there. Then we have divided by, And we have, instead of making this division, we can use, since we are dividing by a fraction, we can use the rule called tip and times, meaning you tip the fraction, you swap the numerator and denominator, and you change the division sign to a multiplication. So this is what we have, and then we can say is equal to the limit as h tends towards 0, and we can simplify that. That is going to be x. When you distribute, you get negative x and negative h over, we still have here x times x plus h, and then this is being multiplied by 1 over h. Okay, so now that we have this, you can see that the x and the x would simplify to 0. So there, the numerator, I still write this because I've not substituted yet. So negative h over, and you have x times x plus h multiplied by 1 over h. So when multiplying fractions, you can cancel common factors if they're in a top-down position. So like there's a common factor on top and the bottom. But you can also cancel common factors diagonally. So do you see there's an h there and an h there? So that cancels. It's like h divided by h is 1. So there's a placeholder of 1. And h divided by h there, still have our placeholder. So this is equal to the limit as h tends towards 0. And we're going to say negative 1 times that 1 that is still there, which is negative 1, over, and here it is this times the placeholder of 1 remaining, which stays the same. Okay, then we are now ready to substitute. We've gotten the function to a point where if you substitute h, it's not going to make it undefined. You see, if you had substituted h here, your denominator would have been 0, and so this would be undefined. So that's the whole purpose of simplifying. Okay, so now we can finally substitute. So we're just saying that f prime of x is finally equal to, say, negative 1 over, in place of h, you're going to put 0, so x times x plus 0, and f prime of x is equal to, we have negative 1 over, now you see x plus 0 is equal to x, so x times x is x squared. And you see we get the answer that we got when we use the rule. So you use the rule just to check and make sure that your answer is correct. Okay, so that is 8.1, and we move on to 8.2. Okay, so we're finally on 8.2, and 8.2 says we have to determine the derivative of this function, so d over dx. So with this, I'll just say just pay careful attention to notation. You will notice that these ones that have this, some sort of derivative instruction, and then you have your brackets. The thing about them is you first have to prepare your function to be derived, or your expression to be derived. After preparing it, then you go ahead and derive it. So just take note of how we're going to write this. An alternative to writing it this way, you could have also written it like, they could have also written it like that, and then, you know, put the function in. So you would do the same thing that we're going to do here in this situation. Okay, so what we do here is we're going to go ahead and say, because we're not deriving yet, we'll keep writing d over dx. And then let's go ahead and simplify what we have here. So the ground rules are, where you have an x, it should not be a surd. Okay, anything that is a surd and an x, you need to kind of change it. But if you have a number that is a surd, it's fine, because that number is just a number. Okay, so you don't have to change numbers that are surds, but you have to change variables that are surds. So let's go ahead. We see here, this has to be changed. Since it's been square rooted, we can square root it. The square root of 4 is 2. And the square root of x to the power of 6 is x to the power of 3. Because what's actually happening is you have the square root of x to the power of 6. This root has an invisible 2 here. You keep the base the same, and you say the inside exponent divided by the outside exponent. And that's how we get that. So that's what we have there. And this is now fine. See, we have x to the power of 3. That is perfect and ready to be derived. Then here, is there anything that you need to change there? No, there's nothing you need to change there, because your square root is on its own. The x is not under the radical, so you can leave it like that. It's just plus the square root of 2, and we have x to the power of 2. Okay, so that's what we have there. Now we are ready to derive, and because we are deriving, I say is equal to, and I go ahead and start deriving. So coefficient times exponent, that gives you 6, and we have x to the power of, subtract the 1 from the exponent, gives you 2. Then here, coefficient, the square root of 2 times exponent gives you positive 2 square root 2. Then x squared minus 1 gives you 1, which we don't have to write, and that is our answer. Okay, so that is our answer there. Moving on to the next question. The next one is another derivative question. We have 8.2.2. We need to determine g prime of x if g of x is equal to this. So let's look at this. Do you see that there is a denominator of x squared? We shouldn't have that. Now, I know normally you would think, okay, maybe we need to move this to the top. That wouldn't work in this case, because I want you to see what's actually going on here. Do you see that you have 3 separate terms and all of them are being divided by x squared? We can actually expand that. So how they came about to be like this is because they were probably written like this before. So it was g of x is equal to 3x to the power of 4 over x squared. Okay, so each of them would have had this common denominator of x squared. That's why when you added them together, they looked like that. And then you'd have had minus 4x squared over x squared, and then plus 6 over x squared. That's why when they added them together and subtracted, of course, when you did that, it became that. And now you can simplify them individually. So we have g of x is equal to, if you divide this by that, you get 3x to the power of 2, and then still have minus there. Divide that, you get 4, and then x squared will cancel. And then here, you just have plus 6 and then x squared. But what we can do to get this to be derived is your x should not be on the denominator. So let's move it to the numerator. And so that makes the exponent negative. Now we can derive. We can say g prime of x. So we have 3 times 2, which is 6. And then we have x. And then we subtract 1 from that is 1. You don't have to write that. Then you have minus 4, of course. So when you are deriving a constant, it becomes 0. Okay, the gradient of every constant, like if you have y is equal to -4, it's a straight line. If you derive this function, it gives you 0, because every straight line or vertical flat line has a gradient of 0. That's the reason why. Okay, so we have that, and then this, when you derive, it's going to be this positive 6 times the -2, which is -12. We have x to the power of -2 minus 1, which is -3. Okay, so I'll just check. It's only 3 marks. So they would have given you a mark for separating, but not really expanding it. They don't give you a mark for doing this. It's the actual act of separating. So a mark for separating, probably a mark for putting that in its correct order, that, and then deriving. So it's 3 marks. You don't necessarily have to put this or write this as a positive exponent. You can if you want to, but at this point it's fine. Okay, so that is that. Moving on to the next question. Then we have the last question of question 8, and it says the equation of the tangent to f of x is equal to 3x squared plus bx plus c at x is equal to 1 is given by y is equal to that. So the equation of a tangent to this parabola, okay, at x is equal to 1 is given by this equation. You have to determine the values of b and c. Okay, let's go ahead and visualize what's going on. So they say the equation of a tangent to f of x, which we can see is a parabola that is concave up because the a value is greater than 0. So we have a concave up parabola, and we have a tangent to this parabola at x is equal to 1, right? And this is the equation of the tangent. I want you to also notice that the equation of this tangent, do you see that? Your gradient is greater than 0. So it is an increasing function. So it's going to look something like, I have the tangent there. I'll just pull that closer, of course. So you have that, and then it's touching the graph once. And we know it's touching the graph. So we know the equation of this tangent. It's y is equal to 9x minus 9. We also know where it touches the parabola. It touches the parabola at the point where x is equal to 1. So as you can see, because it's on this line, we can even find the y value. And then they also told us the equation of the parabola. Okay, so we have the a value at least. So they want us to find b and c. Okay, you see, this has to do with equations and simultaneous equations, really. If you have to find 2 variables, you will need 2 equations. So we're going to have to see how we can form these 2 equations. So since this is the equation of this function, in order to form this, I can see a way of, first of all, it would be helpful to find the y value of this. Okay, I can see a way that we can use the information that we have been given twice to form two separate equations. But I'm going to go ahead and find well, it's not really necessary. Let me show you. So you see, the powerful thing they gave you here is telling you that this was a tangent to this parabola. I want you to understand that the parabola, at different points, it has different gradients. So different gradient here, right? But the thing about a tangent is that a tangent is a straight line. And so its gradient is constant, okay? It doesn't change like a parabola. So because its gradient is constant, we already know the gradient of the tangent, it's 9. So because they meet, right, the tangent and the parabola, they meet at the point where x is equal to 1. Let me get rid of this. We don't really need this now. So because they meet at the point where x is equal to 1, we know that at this point, their gradient is exactly the same. So here's the first equation we can form from that. Knowing that their gradients are exactly the same, what I would do is I would attempt to find the gradient of f, because that's what I'm saying. I'm saying the gradient on f and the gradient of the tangent are the same at this point. So find the gradient of f. It's f prime of x is equal to, we say 3 times 2, which gives us 6. We have x, you subtract 1 from your 2, you get a 1, and you don't have to write that. It's invisible. Then you have here plus b. You see there's an exponent of 1 on the x. So you say b times 1, which is going to give you your b plus b. And then when you have your x, you see it has an exponent of 1. When you subtract that 1 from it, it becomes 0. Anything to the power of 0 gives you 1, and the b times 1 will just give you b. So this is what you get when you derive, when you try to find the gradient of the parabola. Now, we're not just looking for any gradient on this parabola. We're looking for a specific gradient. We're looking specifically for the gradient at this point. And we know that the gradient at this point is 9, because that's the gradient of your tangent. The tangent and the parabola have the gradient, the same gradient at that point. So what we're going to do is, before actually substituting the gradient, I'm going to say I'm specifically looking for the gradient of f at a particular point where x is equal to 1. That's what I'm looking for. So I'm going to substitute 1 into that. So substitute 1 plus b, you really just get 6 plus b, right? That's f prime of 1. Now the thing is, we already know what the gradient is at this point. That gradient is 9. So I'm going to substitute it into the gradient. F prime of 1 is speaking about your gradient of f at the point where x is equal to 1. I know that gradient is 9. So I'll rewrite that, and it's equal to 6 plus b. As you can see, we're already going to solve for b. Take 6 over, that gives you 9 minus 6, gives you b. And so you know that b is equal to 3. There we found our first expression. So our first equation technically. Now, what can we use to find the second equation? Well, it's quite simple. All you have to do is, why don't you just find the y value of this point? Once you find the y value of this point, substitute the x and y value into your graph of f, since this point lies on the graph of f, and then you'll find c, because you already have b. Okay, so that's the second thing we can do. So let's go ahead and find the y value. We can find the y value because it lies on this graph. So we say y is equal to 9, and then substitute in place of 9, 1, then minus 9. So y is equal to, that's 9 minus 9, which is 0. Okay, so that's the point. The point of contact, okay, with the tangent and that graph is 1 and 0. Now we're going to substitute this into our equation of f. So the y value is 0. I say 0 is equal to, and the x value is 1. So 3 times 1 squared plus, and we know what b is, it's 3. So 3 times 1 plus c. That's what we're looking for. And now we can go ahead and find this. So this is equal to, we have 0 is equal to 3 times 1 squared is just 3. Plus 3, which is 6, plus c. Take 6 over, negative 6 is equal to c. So there you have c and you have b, and that's actually what they asked you to find. So that is that question, and that is the end of question 8. And then we move on to question